Hello everyone, welcome to Code Web India. So in today's video, I'll try to explain this lead code problem, cousins in binary tree. So we're given a binary tree and we need to find that whether these two nodes x and y basically are cousins in this binary tree or not. So x and y are values that are present in this binary tree and we need to find whether they are cousins or not. So before we go forward with this problem, we need to ask ourselves what cousins are. Two nodes are said to be cousins in a binary tree if they are at the same level and they don't have the same parent, right? So imagine this binary tree in example 1. 2 and 3 are not cousins. They are actually siblings because their parent is same. Now in this example 2, we can see that 2 and 3 are again not cousins, they are siblings. But these 4 and 5, they are basically cousins because their parents are different but they are present at the same level, right? So these are basically cousins. That's why we return true in this particular case. Now let's go to the example 3. 2 and 3 are not cousins, they are siblings because their parent is common, and 4 and 3 cannot be cousins because they are at a different level. So we know two things about cousins. They have to be present at the same level and their parents should not be equal. So the idea behind solving this problem is to either use DFS or BFS. So let's just see how DFS will help us and how BFS is different. So in DFS, the idea is to traverse each node first to the last depth of it, basically return. But imagine a scenario that we are given these nodes, right, 4 and 3. So what it will do is basically it will start from here, then it will go to 2, then it will go to 4, then it will try to go to the next iteration, but it is null, it will return. Then it will return, then it will return to 1, and then it will go to the right side. So imagine in a normal worst case scenario, we know that the cousins have to be present at the same level, but it is basically traversing to the last depth of 4 and then returning back. So we are doing unnecessary work. So it is not required. So DFS is not ideal for this question. I'll say BFS with early stopping is very useful. What early stopping means here is basically we know that the cousins have to be present at the same level, right? So only 2 and 3 can be considered as possible solution for this particular question because they are at the same level. 2 and 5 cannot be considered because they are not at the same level. Hence DFS will not be ideal and that's why we use BFS. So the idea is to use BFS, okay, but how about we separate the siblings from the cousins? That's the most tricky part about this questions because at same level there might be four nodes, right? Right, we have two nodes here, right? We might have two left childs here also. Then how do we separate the siblings with the cousins, right? Siblings are basically the nodes at the same level that have the same parent. So imagine that we have a node like 9 here. So 9 and 4 will be at the same level and 2 is the same parents, hence they are siblings, right? And if imagine we have a node 7 here, the 7 and 5 are at the same level and 3 is the common root. So they are also siblings, 7 and 5. But how do we separate that fact? Okay, so in BFS, we know that we go from the root node to the next node to the next level, level by level, right? We insert one, then we insert two and three, then we insert all the left child and the right child inside the queue, right? So the idea to separate between the cousins and siblings is basically use null value as a dereference, right? Insert null whenever we have inserted the left child and the right child. So basically what will happen is 1 will get inserted into the queue, okay. Then 2 and 3 will be inserted into the queue, then we insert null, okay. Then the left child, imagine 9 here will be inserted, then 4 will insert it, they'll be insert null here, then 3, then 7 and then 5, then we insert null. So what this null will do is basically we check if we encountered a null, basically the value that we have seen that matches here like 4 can never be the sibling of the value that we are about to encounter. So this will help us a lot. So I'll code it through and I hope you understand it. Okay, so the basic idea is to make use of a queue. Yes, so we use queue like this. We insert the root node inside the queue. Then we check basic condition while queue is not empty. Okay, then we make use of two variables, cousins and siblings, because this is the only tricky part about this question that we need to solve. Then we basically get the size of the queue. Then for that size we insert this size basically denotes here the number of items that are present at particular level, right? The number of nodes. So the size when we insert 1 will basically be 1. When we insert 2 and 3, it will be 2. So it will only iterate through 2 times, right? Okay. Then we extract the node that we get from the queue. Now comes interesting part, right? I told you about the null operator that we insert inside it, right? So we first check, hey, if this node that I have just extracted from the queue, is it null? So if it is null, that means they cannot be siblings. That I told you about this particular case, right? If we insert null between the left, right childs of two different nodes, right? So null will come here, after the 4 and the 7, imagine the 7 here. So whatever value we have must have got from here can never be the sibling value, right? So we set the siblings to false. Else we check if we have encountered a value that is equal to the given value that we want. Okay, so now again we check if they are not cousins. If they are not cousins, so obviously they can either be siblings or they can be cousins. So we set true to that. Else, if they are cousins, simply we return the value. They should not be siblings because it will return true and then we are done. Okay. Now after that we need to insert the left child inside the queue and the right child inside the queue. And finally, as I told you, after each level, we need to insert null so that we can separate them. And finally, we exit from this loop. And there might be a certain scenario that we might encounter that we are given these two nodes like this x is equals to 4 and y is equals to 3. So they might be at different levels, right? So, and if the cousin flag is somehow true, we return false. Then finally, we return false. Okay, so let's just run this code. Yes, it is working fine for this particular example. Let's just submit it. Okay, it is working fine, 0 millisecond, 100%. Yeah, so this is probably the best solution that I can think of about solving this cousins in a binary tree problem. So it was asked in Amazon and DE shop. So it is a very important problem. It is given easy, but it is not easy because we have to handle that particular tricky siblings and cousins part. So I hope you like this video. Thank you so much.